Morning, we will start soon. Let's just wait for another 5 minutes. We will start very soon. Let's just wait another 5 minutes. Okay, everyone, I posted homework 3 on the canvas. Let's start. The homework 3 is about the cache and DRAM and virtual memory. Today we will talk about DRAM. So we talk about the SRAM, which is the static memory, static RAM before. The static RAM is very simple. You have a two converter. The input of a converter connect to the output of the other one. So in this way, you can have a static state besides the access transistor. Totally, we have a two transistor here for one single inverter, another two here for the other inverter, and two access transistors. So totally, we have a 6 transistor for each cell to store one single bit. This is very expensive because we need a 6 transistor here. There is another type of memory which is widely used in the current main memory, which is so-called dynamic memory. Dynamic memory use only one single transistor. plus one single capacitor to store the data, to store one bit. And the SRAM consists of only single conventional inverters. So it's a CMOS compatible, which means that you can fabricate your logic gates, for example, a NAND gate, an XOR gate, and the SRAM together on the same die without any extra steps of the process technology. But the DRAM is different. DRAM is not a CMOS compatible. DRAM process technology is heavily optimized for the density because of this capacitor, and also the transistor. We need to keep the leakage power of the transistor at a very low level, and we also need to, fabricate a very high density capacitor, which can have a relatively large capacitance to store the single bit. So this is the SRAM. This is the DRAM. So you can see that the DRAM has only one single transistor and one capacitor. This is the capacitor. You can see the capacitor is actually very small here. By training this, when we activate this word line by setting it to 1, this gate is closed, so you can actually send the current or charges through this gate into this capacitor. This capacitor can store some charges, some current for you. If you have those charges or currents, then it's 1. Otherwise, if it has nothing, then it's a 0. So it's very simple. It's just a capacitor. But the capacitor, how to make a capacitor on the die is very difficult. Like this figure shows, you need to dig a very deep hole on the die. Nowadays, when we talk about a DRAM, we prefer 64 GB. How many holes you need to dig on the die? 64 multiply 8 G. You need these amounts of this structure on the same die. Not necessarily the same die, maybe 8 dies or 16 dies, but still the number is very significant. And you need to make sure that all these structures have the so-called uniformly have a uniform structure. They have about the same depth, same dimension. You have to guarantee that. Otherwise, some cell will. There is another feature means spontaneously some charge will leak through this gate, no matter it's closed or open. So if you make the capacitor not uniform, then some cell will leak the charge faster than other cells. So some cell may lose the content, while other cells may still have the content. So this is very, difficult. And because we always have new process technology, now we talk about 22 nanometer. Maybe soon we will have a 10 nanometer. Maybe now we already have 10 nanometer, maybe 8 nanometer. By this so-called process technology shrinking, this distance is reduced. So the distance between these 2 points is reducing. In order to maintain the same capacitance, we need to dig a deeper hole. So now the ratio between the depth and the dimension maybe is a 600 to 1. I believe the tallest building on the earth should have a smaller, this ratio. The depth or the height, the ratio between the height or the depth and the dimension should be smaller than this value. So you can see that how difficult to fabricate this capacitor. Again, by the same array structure, we can have one array. So we have multiple rows and multiple columns. Each column is one single bit line, which connected to the sense amplifier. Each row is just one. We learned the concept of page, right, in the virtual memory. One page is typically 4 kilobytes. And we call one row is one page. Why? I will explain why. So you can see that because SRAM requires 6T, DRAM requires 1T plus 1C. So DRAM is more denser than the SRAM. How to read something from this array? The first step is to activate this row. Activate this row means I send a 1 here by this decoder. I give a 1 here so that all the transistors here are closed, which means that the cell is connected to its corresponding bit line here. I can either set this bit line to 0 or to 1, so that I can modify the content. Or I will explain the read operation in the following slides. So the low-level organization, particularly the array organization, is similar to the SRAM. Cells are only single-ended. So here is a floating capacitor. This is the reason why it's so-called a single-ended. Only the other end is connected to the transistor and connected to the bit line. The other end is floating. And we also have so-called a row buffer. I'm sorry. This is the row buffer. Row buffer is a small buffer which can temporarily store some data for the row, for one single row. And we call one row typically a page, because traditionally one row is 4 kilobytes, but now one row maybe 2 kilobytes, 1 kilobytes. You can easily, consist one. You can easily form a row, 4 kilobytes row by multiple DRAM rows. Now, one DRAM row is not equivalent to this page concept, but traditionally they are the same. So now they are not necessarily the same. Reads will read the, read will read the entire row into the row buffer. For example, this row will be activated, and then all the content will be sensed by the bit line, by the sense amplifier, and then the content will be stored in the DRAM row. Row buffer here. And since you have a row buffer here, you also have a so-called column max. Column marks can help you to select only a part of the data, for example, this piece of data, and send this piece of data out of this array. Next time, maybe if you read this one, this piece of data, it will, select this one and then send out the array. But the problem is that only if you want to read the same row, this row, you can read some data from the row buffer. Otherwise, you have to active this row again. I active another new row and sends the data, the new row data to the row buffer to replace the old data here. So if you have a lot of requests to the same row, you don't need to active the row anymore. You just read the data directly from the row buffer. This is the reason why reading from a row buffer, is faster. Similar to reading to a cache line, reading something from the cache. Then I will explain the read operation on DRAM. So this is the access transistor. This is the capacitor. The left part is the scenario of 1. The right part is the scenario of 0. So how to read a 1 and how to read a 0. So you can see that we charge the bit line voltage, which is the bit line. The vertical line is a bit line. Before any read operation, we charge this bit line, this bit line. To 0.5 VDD, no matter you want to read a 0 or read a 1, because you don't know whether it's a 0 or 1, so you do the same. You charge the bit line to 0.5 VDD here. And then you active the row. You enable the row. The so-called enable the row means you send the 1 here so that all the transistors here are closed, which means that this capacitor can be connected to this bit line. This capacitor can be connected to this bit line. Now they are connected. So you give it some times so that they can perform so-called charge sharing. The charge sharing means if this is a 1, which means that you have some charges in this capacitor. Okay, so this is the 1 because this is a capacitor voltage. Originally, it has 1, so it has a full VDD. And your bit line is a 0.5 here. When this guy is closed, this is 1, this is 0.5. Then on this bit line, the voltage will get higher. It will get close to the VDD, but you can never reach the ADD. You can never be the same as the VDD. Why? Because this is 1, this is 0.5. If you use 1 plus 0.5, you get divide and then divided by 2, you get 0.75. It's never a 1 again. So the voltage here will increase a little bit, but the voltage here inside the capacitor will decrease a little bit, but it's still larger than 0.5. It's still larger than 0.5. Again, in order to reliably store the data, even it's larger than 0.5, you cannot use it anymore. So the read operation just destroy that 1 value. So let's see what will happen on the 0 case. So you pre-charge the bit line to 0.5, and the capacitor, this guy has a 0 voltage here. When you enable the row or the word line. Because this is a 0, the charges on the when it's closed, the charges on the bit line will flow into the capacitor. So the voltage on the bit line will decrease. It will never reach 0, maybe larger than 0. But the voltage in the capacitor will increase a little bit. Again, after this read, the 0 here is not a 0 anymore. So the read operation destroyed the 0 value. By sensing the difference between the 0.5 VDD and the stable states here, we can distinguish whether this is 1 or 0. So this is the progress of the destructive read operation. Any question on this? So based on the content of the capacitor, we have a different results on the bit line. If it's a 1, then the bit line voltage will larger than 0.5. If it's a 0, then the bit line voltage will smaller than 0.50. But we will always charge the bit line voltage to 0.5 at the beginning of the read operation. The only difference appears at the end of the read operation. By the difference, we can know, okay, this is 1 or 0. So after a read operation, the data inside the DRAM cell are gone, but the row buffer have the data. Now the data is all in the row buffer. So if the data is in the row buffer, we call this row is open. If the data is in the cell, we call this row is closed. So the content after the read operation inside each cell is destroyed. But we have the content inside the row buffer. So if we decide to close this row, we need to do a so-called operation, which is a so-called restore. So we need to do a restore operation before another read operation. Before the restore operation, we can read the data out of the row buffer if you have some heat in the row buffer. So if the data is in the row buffer, you can read any data from the row buffer. But if you decide to activate another row, which is maybe this row, you need to do the restore and then fetch the content of this row to the row buffer. There are another feature of DRAM is gradually the content will leave, the charge will leak away. This is so-called why is so-called dynamic. You need to periodically refresh the cell, rewrite the content. So the rewrite operation, the so-called refresh or rewrite operation is very simple. You just read the cell. When you read the cell, the content in the cell is destroyed. The content will be read into the row buffer, and then you do the restore. So the so-called refresh is a read operation and a restore operation. So this is the voltage of the capacitor if you do not do anything on the capacitor. So maybe at this time, we need to do the refresh. For the refresh, we have a different policy. The first one is that, okay, I know that I will do the refresh I have to store everyone. I have to store everything, and then I just do the refresh one line by line until I done for maybe 64 GB content. So I just make you work, make all the application work until I find out I have to do the refresh. I cannot wait anymore. Then everyone stops and I will refresh maybe 64 GB data. That's very, how to say, that's very slow because refreshing these many data are really slow. All you do the distributed refresh. So you have so-called empty space. You always refresh this empty space, and you do some data movement so that some application may have available space, but some application may have to um, do the refresh. So for your mobile phone also have the DRAM. When you try to inactivate your mobile phone, although your screen is black, but the DRAM also refreshes itself spontaneously in a low power mode, so that the content in your memory in the memory of your mobile phone will not lose. Your mobile phone even can even turn off the memory controller, but DRAM chip itself will do the self refresh. Self refresh is a very low power consumption. So then we will introduce the typical procedure of a read operation. All the read operation is initialized by the CPU. And then the CPU will send the request to the memory controller. Your request is very simple. For example, you move, no, not move something. I'm sorry, the load something, load something, load something to R1. The CPU just send this request to memory controller. Memory controller will translate this instruction to what? To the command which the DRAM can understand. The DRAM can only understand, for example, active one row, sends the data to the row buffer, restore, refresh, or use column max to read a part of the row buffer. So DRAM can only understand these simple commands. And your memory controller actually a translator which can translate the real instruction to the DRAM instruction. And then the memory controller will first send a activation, which means you use the row decoder to select one row, active one row. And then it will send a command named row address drop, which means that active which row. So you want to active this row, and you need to give this row's address. So when you so-called active this row, you actually read the entire row's content to the sense amplifier, to the row decoder. before the memory controller knows which column, which 64 bytes you need. So it just reads the entire row, 4 kilobytes, let's assume, into the row buffer. And then the memory controller will send out a command named column address strobe, which you send a column address to this column decoder and then select only one portion of the data in the sense amplifier and send only this small portion to the buffer and then return to the memory controller and then return to the CPU. Yeah, data transfer means you send this small piece of data to the memory controller. And then the memory controller will send the data back to the CPU. This bus is also called a front side bus or something, FSP. This is FSB. This is a very important metric if you do the overclock things on your computer. So the CPU, of course, prefer a faster bus. So let me summarize the whole process. First, the CPU initialize a read operation. And then it send this read operation to the memory controller. Memory controller translate this maybe RISC instruction to DRAM instructions. And then memory controller send a activation command, which is also called a row address strobe command. So the DRAM can activate one row and sends the entire row to the row buffer. And then the memory controller will send the column address strobe, which will select only a part of the row and fetch that piece of data, that's a small part of the data, to the memory controller. And then the memory controller will return the data to the CPU. This is the general case, which is a E2 case. So the memory controller need to first send a row address strobe and then the column address strobe, 2 steps. Assume that no one accessed your DRAM before. At this time, maybe CPU want to read another piece of data, so the CPU will do everything again, and the memory controller find out, okay, the new piece of data is actually in the same row. So in this way, it only send a cast column address strobe, which means that you have a row buffer hit. So if you have a row buffer hit, you just need to send a single comment. That's easier and faster. Maybe at the last CPU want to read another new piece of data, and memory controller find that this piece of data is not in the same row. So the memory controller need to send a restore first, pre-charge. The pre-charge or restore indicate you need to write your content back from the row buffer to the row itself. And then a new row address strobe, and then a new column address strobe. So you have 3 different options. You have the normal option, standard option, you have the the row buffer hit option. You also have a row buffer miss option. In this way, you can calculate the DRAM latency. either the DRAM latency always have A, B, C, D, E, F parts, but the E have 3 different cases. And 3 different cases have a huge impact on the value of the final DRAM latency. So this is the timing of the DRAM RAID. Row strobe, CAS, column row strobe, address strobe, and row address strobe, I'm sorry. And then you have some piece of data. This is normal case. Row address strobe, column address strobe, and then you have the data. This is the data bus. This is the comment bus. This is the enable signal of a row strobe or row address strobe and a column address strobe. You can see this is normal case. In the normal case, you always have a row address strobe, column address strobe, and then you have the data. This is the page buffer. I'm sorry. This is the row buffer heat case. You have only one row strobe, open one row, active one row, and then you send a column address strobe. You have your data, and then another column row strobe. You have your data, and then the last one, and then the last piece of data. You have only one row address strobe in if you have a lot of row buffer heat. Now the DRAM, the SDRAM indicate a so-called synchronized DRAM. The so-called synchronized DRAM means it has a clock. So you have a clock here. When you have the row strobe, row address strobe, column address strobe, you can, utilize this clock signal to have multiple pieces of data. So in this way, you don't need to each time send a CAS here. You can just say, okay, I want to a consecutive, maybe several bytes, and then it will give you all the data here. You can see that the data bus pump the data at the rising edge of the clock. Okay, so it's a slow because you only can utilize the rising edge. Now we call the so-called DDR means we not only take advantage of the rising edge, but also take advantage of the falling edge. So on the falling edge and rising edge of a clock, we can send out the data like this. So you can see that if each block indicate 8 bit, then we just double the data rate in this way. This is a signal, data bus signal, changing from low to high, from high to low. You can see that it also requires some setup time because we hope the rising edge can be like this. We hope we have a very steep signal, but actually, it increases gradually and slowly. So if we have a very steep signal here, if we have a very steep slope signal here, the area of this center circle will be larger. Because this is a data bus, typically we call this data I. We hope that the I size is large. if the DRAM has a small I, like me, then the signal quality is not good. So people hope that they can have a large I. Large data I indicates you have a better signal quality. Signal is an analog concept, so it's not a 1 and 0. You can see sometimes here you have a 0.5. You hope that the appearance of 0.5 can disappear. The occurrence of 0.5 can disappear very fast. So that they want to adjust the distance between this point and this point. Sometimes they intentionally, prolong the path. They have a lot of these things so that they can, make sure that on each path they have the same capacitance, the same resistance, because these resistance or capacitance will have a huge impact on your signal quality. So sometimes they just intentionally increase the capacitance and the resistance by using, these shapes. They want to increase the distance between 2 points. And we also have some concept of bank in the DRAM. A bank is a piece of DRAM which can be independently read and write. Either this is the physical address, this is your 64 bytes, or your memory line size. Either you can store your data, have the data layout like this: word 0, word 1, word 2, and then word n-1. So different words is actually in different consecutive different words is actually in different banks. So in this way, you can take advantage of the spatial locality, and you can also take advantage of the parallelism. For example, from the spatial locality perspective, once in one request, you prefer to read this guy, and this guy. So in this way, you can read them from different banks. Different banks can independently serve you. So you have a very good parallelism. But again, each bank has a row buffer. You just serve one request by all the banks, but you didn't take advantage of the row buffer inside this bank. Because next time, it's very likely you read this row, these words. In this way, you cannot read it from the row buffer because your row buffer stored these words. So this is the physical layout of your DRAM. This is so-called DIMM, D-I-M-M, DIMM. You have a lot of chips, DRAM chips on the DIMM. Each chip have a lot of arrays in each chip. And we also have ECC. Some chips are stored the ECC. The ECC can protect some accidentally flipped because of the radiation. And we also have so-called channels. You can consider the channels as a memory controller. Either this is only a single channel. One memory controller can control one DIMM. Or one memory controller can control two DIMM. They share the same command bus, but have different data bus. Or you have two separate memory controller. This is also called a true double channel design. You have a separate command bus and a separate data bus. In the second case, maybe the command bus can be a potential bottleneck. Again, there is a trade-off between the parallelism and the spatial locality. You can either have data layout like this, separate your words, consecutive words in different banks, or you can store the consecutive words in one bank. For example, 0, 1, 2. If you want to read these words, you can just activate one bank and utilize the row buffer to provide low latency. So by different address mapping, you can have a different data layout. So this one is the I'm sorry. This one is the concept that we just talk about here. Because the consecutive words are actually stores, not consecutive words. Consecutive offsites or memory line are stored in different banks. And this one is the later one. Consecutive memory line is actually stored in the one bank, so that you can take advantage of the row buffer. This guy, you prefer larger parallelism. You can use multiple bank to serve one single request. And then you also have open page mapping and closed page mapping. Open page mapping means you know that you will have a lot of heat inside one page. So in this way, you prefer this guy, because when you open a page here, you can have a lot of following requests go to the same page. Or you have a closed page, which you anticipate that you will have no heat. You prefer higher parallelism in this case. So by different application, you can choose different mapping schemes. And this is the CPU to memory connection. This is your CPU. This is a front side bus. The north bridge is your memory controller. So your memory controller can go to the DRAM. And your memory controller can also, communicate with your GPU. Of course, this is a very old GPU bus. Now you use PCIe Express. The south bridge only in charge of some very slow devices like these. The north bridge is your memory controller. So this is the motherboard. And you can see this is the CPU. And this is the memory controller north bridge. They are very close. This is south bridge. So you can actually, have a one-to-one mapping to check this figure and this figure. They are the same. Now, more advanced CPU design actually integrate the north bridge, the memory controller on chip. So your CPU includes the north bridge. Now you only have a south bridge. Because the memory controller becomes more and more important. You can also do some scheduling here. You have a read queue and a write queue, and you have to do some lightweight scheduling. For example, the first request go to row A, the second request go to row B, and the third request go to row A. If you strictly following the order, first in, first out order, then you will have no row buffer heat because the first and the third request go to the same row, but the second go to another row. You have to open row and then close it, and then open another row and then close it, and open the first row again. But if you reorder the second one and the third one, you can have a row buffer heat. So the memory controller can also do some lightweight schedule. This is the jobs the memory controller can do. Connect the CPU and the DRAM, serve the cache misses, possibly from multiple core, do the DRAM refresh, row buffer management, address mapping, and some lightweight request schedule. And you can so-called row buffer mapping is the open row or closed row and a closed row policy. Either you prefer that you may have a lot of heat, so after a read operation, you leave the row open. So you hope that next time you have another heat. Or you anticipate that you will not have no heat, you just close the row after each read operation. This is the difference.
Professor, I had a question.
Yes.
Does the memory controller also connect to like the chipset or like other peripherals like the PCIe, or is that something else?
Yeah, now the PCIe is not connected to the memory controller. The PCIe called is connected to a hardware component named Direct Memory Access (DMA).
Mm-hmm.
So the PCIe now is on this side. It's connected to the, so for example, now it's your GPU here.
Yeah.
But your GPU is not managed by this low soft rate. You have a more advanced device named the DMA.
All right.
The DMA can move the data from your GPU to the memory, and then
All right.
your CPU can read something from the memory.
All right. Thank you.
And then about the scheduling, we have a different policy, which is a first come, first serve, which basically the FIFO, the style, FIFO style, or the first ready, first come, first serve, which you consider the row buffer heat. You reorder the request in order to increase the row buffer heat. So you find some row buffer heat. And then schedule skip the older conflict request. By conflict request means the request go to different row buffer. So the first ready, first come, first serve only consider the row buffer heat. This is also can be translated prioritize the column changes. The column changes means you request the data in the same row but different columns. You don't prefer the row change. Row change means you request another row. So they have different method to say the same thing. But the kernel thing here is schedule for row buffer heat if two non-consecutive requests go to the same buffer, we just reorder them and make them consecutive and go to the same row, same row. The request is also very difficult because the memory controller need to obey a lot of timing constraint. What's the timing constraint? The timing constraint is this. Only if you send the activation maybe after 10 cycle, you can send, I'm sorry, only after you send out the activation 2 cycle or 3 cycle, you can send the column address strobe. They have some fixed delay and fixed limitations. And the memory controller need to remember all these constraints. This is the reason why the scheduling is difficult. Even sometimes you have a buffer, but for some timing constraint, you have to give up the heat. And also you need to simultaneously track all the resources like channel, bank, rank. You have a lot of devices to manage by only one single memory controller. This is the reason why people want to add another memory controller, so that the memory controller will not be the bottleneck. So what if the memory is very slow? And then the time, the latency will be dominant by the memory latency. But you can still explore the bank level parallelism. This is also called a memory level parallelism. The memory level parallelism is a useful way to improve your performance. So here is some example. If the heat latency, cache heat latency is 10 cycle, memory access latency is 100 cycle. If the miss rate is 50%, we use that. We have this equation in our homework 3. So 50% heat, 50% miss, 50% heat will have a 10 cycle as the memory access latency. The other 50 has 100 cycle. Totally, this is the average latency. So if we can simultaneously serve multiple memory requests, then we can significantly improve the average latency. If we can simultaneously serve 4, then we can directly use this value divided by 4. The answer is 14 now. So improving the memory level parallelism is very important, particularly for the big data applications. The MLP, memory level parallelism, is an indicator for the performance. So you can see how to improve the memory access latency. We have a different way. Either we increase the cache heat rate, or we improve the memory level parallelism, or we can do some prefetching. Prefetching means I can do some prediction on the future memory access. I can pre-issue that read operation. So when you actually want to have that piece of data, the request that has returned, you don't have to stop and you can continue to run your data. Any question? So if no question, we can stop today. Thank you very much.
Thank you.